All right, if you're like me, people often ask you, what's the matter? What's the matter? And I say, like most of you, everything! Everything that has mass and takes up space, which boils down to everything except a vacuum and energy. So matter and that's why I'm so happy, because everything's matter, and as a chemist, I get to study everything. Because chemistry... that was supposed to go cool ninja off to the side, but it didn't! Because of chemistry, as chemists, we study matter, and one of the things we do when we study matter is we classify it to make it easier to talk about and easy to understand conceptually and mathematically. That means we have to divide matter. We classify matter into two broad categories on the basis of whether or not they can be simplified by physical means. The first group is mixtures. Mixtures are a physical combination of two or more pure substances. They can be simplified by a physical means to a pure substance. A pure substance is any substance that cannot be simplified by physical means. My favorite example of the difference between pure substances and mixture is one you may have done at home. Anybody ever made rock candy at home? How do you make rock candy? You get a container of water, and into that water you add sugar. You keep adding sugar to the water until you have a really concentrated mixture of sugar and water. How do you then separate that mixture of sugar and water? You leave it out overnight, and overnight what happens? The water evaporates. Right? And evaporation is a physical process because you have liquid water going to gaseous water, so it's a physical process, and you're left behind with just sugar. So in this example, our sugar water is a mixture that we simplify by the physical means of evaporating our water off, leaving two pure substances, sugar, because it wasn't simplified by a physical means, and our other pure substance, which happens to be water. And that's the difference between pure substances and mixtures. Write down willow, W-I-L-L-O-W. Write down willow. We divide pure substances into two important categories: elements and compounds. Once again, their relationship is defined by simplification. Compounds can be chemically simplified to elements. Elements cannot be chemically simplified. Let's start by looking at each in turn. Elements cannot be simplified by normal chemical means. There is nothing we can do to an element chemically to simplify it. The simplest form of an element is the atom. It's the smallest unit of an element with all the properties of that element. We represent elements as chemists using what are known as elemental symbols. Elemental symbols Elemental symbols are abbreviations of one or more letters. When writing an elemental symbol, there can be only one capitalized letter, like the Highlander, right? There can only be one capitalized letter when writing an elemental symbol. Hopefully you have a periodic chart printed out and you're looking at it. This periodic chart's full name is the periodic table of the elements, meaning that anything you see listed on that periodic table is an element. You also see, when looking at that periodic table, that every little square has an elemental symbol on it. Some of these elemental symbols are quite logical. For example, the element carbon is represented by the capital letter C. The element sulfur is represented by the capital letter S. The element iodine is represented by the capital letter I. If you look at every square on your periodic table, in the center of it, you will see the elemental symbol. It's very important to remember that capitalization is important when it comes to elemental symbols. The classic example is sulfur, iodine, and silicon. Silicon has the elemental symbol capital S, lowercase I. If I wrote that, I'm talking about a compound made from sulfur and iodine. If I write that, however, I'm talking about the element silicon. So it's really important that you keep your capitalization straight. Another classic example is if you go to your periodic table and look up the element cobalt. Cobalt's on your fourth row, number 27 there. You'll see that its elemental symbol is capital C, lowercase o. If I want to talk about cobalt, I write that. If I want to talk about carbon monoxide, which is a compound formed from one carbon and one oxygen, then I write capital C, capital O. So those capitalizations make a huge difference. Mastering Chemistry and any other homework program out there ruthlessly enforces capitalization, as I do on my exams. Cobalt, capital C, lowercase o. Carbon monoxide, capital O, capital C, capital O. So pay attention to those capitalizations. In addition, elemental symbols can do some fun things. Well, things like oxygen, carbon, sulfur, iodine, and silicon, you can easily see where those elemental symbols come from. Other elemental symbols are actually based on the old Greek or Latin name. For example, iron has the elemental symbol Fe after ferrous and ferric. The old Latin names. Iron, Fe. You'll see some other ones like that. For example, silver has the elemental symbol Ag. Gold has the elemental symbol Au. Now these unusual elemental symbols are actually easy to remember after all. If you were expecting somebody to give you a gold ring and instead they give you a silver ring, you're going to go, ah! But if somebody catches you by surprise and gives you a gold ring, you're going to go, aww. Right? Easy enough to remember. But you will see that looking at the periodic chart that some of those elemental symbols are based on how we roll with them in English, and others are based on older Latin terms. Why don't you write down spike? Why don't you write down spike? S-P-I-K-E, spike. A chemical combination of two or more elements in a fixed ratio is a compound. Compounds can be chemically simplified into elements. Classic example of a chemical compound would be carbon dioxide and carbon monoxide. These two compounds help us represent and discuss the definition of a compound. The definition of a compound says that it's a chemical combination of two or more elements in a fixed ratio. The identity of a compound is determined by both the elements that make it up and their ratio. In carbon dioxide, you have one carbon and two oxygens. In carbon monoxide, you have one carbon and one oxygen. Different ratios, different compounds, and much different properties, right? Our body can clear carbon dioxide without any trouble. Carbon monoxide, however, adheres very rigorously to our heme protein and can lead to a rapid asphyxiation. So the ratio makes a big difference. Another example of how ratio is important I have over here. This first compound with two carbons and 6 hydrogens and 1 oxygen is ethanol. Ethanol is drinking alcohol. This is the alcohol that you consume when you drink a beer. It only kills you slowly, right? And only if you do something really stupid. This down here with 1 carbon, 4 hydrogens and 1 oxygen is methanol. Notice, just like ethanol, it contains only 1 carbon. It Just like ethanol, it contains only carbon, hydrogen, and oxygen. However, methanol, because of that different ratio, is metabolized by your body differently and actually will kill you rather rapidly and is highly poisonous. A chemist and his friend go out to a restaurant. The waiter asks them what they want to drink. The chemist says, showing off, "I'd like a glass of H2O. His friend, wanting to play along and be like the cool guys, after all, chemists are always the cool kids on campus, says, "I'd like a glass of H2O too, please." They receive their beverages, the friend drinks his and collapses over dead. H2O, water. H2O2, hydrogen peroxide. By the way, that stuff you buy at the pharmacy, it's only 3% hydrogen peroxide. And that's enough to bleach your hair and cleanse your wounds, right? You can imagine what the concentrated stuff does to you. It occurs to me that I haven't actually talked about how we express the identity of a compound. We identify a compound using a formula. A formula, often referred to as a molecular formula or a formula unit, consists of elemental symbols, telling you what elements are in the compound, and then subscripts that tell you the ratio of the elements in the compound. And when I say ratio, that ratio is the ratio of atoms of that element. For example, if we're looking at water, water would have 2 atoms of hydrogen for every 1 atom of oxygen. So these numbers down here belong to the element right there. Just in case you're in doubt about that. Another thing that you often see in a compound's formula is it will sometimes tell you connectivity information. It turns out, and this was something we'll go into a great detail if you carry forth with chemistry, that the properties of a compound are often determined by its shape and its connectivity. And when we write a compound, such as methanol, like this, we're telling the person reading how the compound's put together. We're telling them that, hey, 3 of those hydrogens are attached to the carbon, but that last hydrogen is attached to a oxygen. So compounds their formula can often provide structural or connectivity information. Alright, but I'm getting way ahead of myself and way too excited about compounds. So before I compound the issue of confusing you, ooh, that was 2/3 of a pun. P.U. Let's move on to mixtures. Okay, mixtures can also be subdivided. Mixtures are subdivided into 2 categories: homogeneous mixtures and heterogeneous mixtures. Unlike the differences between elements and compounds, the differences between homogeneous and heterogeneous mixtures simply has to do with uniformity. A homogeneous mixture is a mixture whose composition is uniform throughout, meaning that it is the exact same in terms of its makeup in all parts. It can be described mathematically because it is uniform in its composition. Therefore, we as chemists like dealing with them. Not only that, but ignoring all metaphysical aspects, all life forms are walking, talking, aqueous homogeneous mixtures. The classic example of a homogeneous mixture is salt water. If you place some salt in a glass of water and you stir it thoroughly, then your first sip of salty water will be just as salty as your last drink of salty water, because the salt has been evenly distributed among the water. Some other examples of homogeneous mixtures are wine and Kool-Aid. I'm covering all age ranges with those last two. Heterogeneous mixtures are not nearly as interesting. Heterogeneous mixtures cannot be described mathematically. Therefore, they're a pain to deal with. They're not uniform throughout. Classic examples of them would be a salad dressing, right? Ranch salad dressing. If you think about it, you pour some on your salad, and sometimes you get some that is loaded with blue cheese, but the person next to you from the exact same bottle will pour some out on their salad, and they've got nothing but the black peppercorn. Not a part of blue cheese to be seen anywhere. Another example would be trail mix. Mixtures can be solids as well as liquids. But if you look at trail mix, is it uniform throughout? No! You don't want to be the first person to grab a handful of trail mix. You get stuck with peanuts and almonds and peaches, dried peaches and dried apricots. You want to be the last person to get some trail mix. Right from the bottom there, where all the M&Ms and chocolate chips have fallen to. Another example would be motor oil in a rain puddle, right? They don't really mix that well, and therefore the top part of it will be much more oily than the bottom part. Those are all examples of heterogeneous mixtures. All right, which of the following are elements? How should you answer this question? Use your periodic chart. If you haven't printed one out by now, print one out. It's really a matter of just going through your periodic chart and locating whether or not these substances are located there. Be very, very careful with the spelling. So if I were you, pause me. Please pause me. I know every single time you don't pause me and you just keep on going and listening to get this lecture over with, but please, I'm begging you, pause me and see which of these are elements and which aren't. Thank you. I appreciate you pausing me, even though I'm sure some of you didn't. Yes, I'm talking to you. Let's go through them real quickly. Arsenic is located in your periodic table there. It is number 33, and just fun factoid, arsenic was about the 5th element that mankind actually purified. I guess people were very interested in poisoning each other very early on. It has the elemental symbol AS. I guess that's because you have to be a real to poison somebody. But at any rate, then you have carbon monoxide. Carbon's on your periodic table, but not carbon monoxide. That's because carbon monoxide, as we've already talked about, is a compound consisting of carbon and oxygen. Now, this is one that I'm hoping to really puzzle you with. Glucose sounds really chemically, and you've heard it before, but that's because it's a compound. It's a compound consisting of carbon, hydrogen, and oxygen. Then you have calcium. Look on your periodic table, second column there, and you'll see calcium, elemental symbol Ca. Next you see phosphate. You have to be super careful with spelling, which is ironic considering, well, you'll discover before the end of the class. But phosphate is not an element. It's not on the periodic table. Now you'll see on the periodic table phos for us. That's an element. Elemental symbol P. But phosphate is actually a special type of compound known as a polyatomic ion. Whoops. known as a polyatomic ion. Phosphate is not on the periodic table. Phosphorus is. Because phos is for us. We should elect him to office immediately. Then thorium. Thorium's a very popular element right now. In addition to being one of the Avengers, thorium's also gaining more and more interest as a nuclear fuel. It has the elemental symbol TH, and it's really hiding down there in your periodic table. If you look at the very, very bottom, those two rows that stick out at the bottom, you'll see thorium starting the second row there that sticks out below at the bottom, and has the elemental symbol TH. Why don't you write down angel? Everybody write down angel. A-N-G-E-L. Angel. All right, this is another one I hope you pause me on. This time you're actually going to do it. 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 Do it now. All right, unpause. First one's a tricky one. It's one of my favorite ones on an exam because people will automatically see the P and want to put capital P. Potassium, if you look at your periodic chart, has the elemental symbol of K, which always makes me wonder about the potassium content of special K. I should look that up sometime. But at any rate, then we have iron. We've already discussed that's an unusual one. Why the giant was so interested in iron, I don't know. Fee, fi, fo, fum, fee, 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 fee. Anyway. Gold, we talked about, as we did silver. Lead's another unusual one. Lead is actually capital P, lowercase b. Oxygen's O, and cobalt, CO. Last example here. On an alien planet, explorers discover a new substance. They label this liquid K. They pour liquid K through a filter and collect a series of small crystals on the filter. What can they conclude about liquid K? Well, is pouring something through a filter a physical means of separation or a chemical means of separation? It's a physical means of separation. So, if when they poured liquid K through the filter, they wound up with a series of crystals in addition to a liquid, and they were using a physical means, it must have been they had a mixture initially. Now we don't know anything about the liquid, we don't know anything about the crystals, but we know initially they were mixed together. Alright, that's it for this lecture. See you on the flip side.